This is Unit 7.1. It concerns work done or energy transferred, and the key idea here is energy is conserved. It's a very, very important idea in physics and science in general. Energy is conserved, it cannot be created, and it cannot be destroyed. So we're going to be looking at types of energy. This is or work done or energy transferred. We're going to be looking at some calculations, the unit used. So although energy or work has many different forms, we use the joule or the kilojoule to measure them all. And we're going to be looking at some particular types of transfer which the board wants you to know about. Once again, key idea is energy is conserved. It cannot be created, it cannot be destroyed. You have to account for it. It will always go somewhere, even if it's not obvious. Now there are a few different schemes for listing different types of energy, but this is one that I like. As a mnemonic, most kids hate learning GCSE energy names, so that gives you magnetic, kinetic, heat and light, by which we understand EM waves, gravitational potential energy, chemical, sound, elastic, electricity or electrical, and nuclear. So we've got a couple of different images to illustrate those here for you. Now, as we've already said, the key idea is energy cannot be created or destroyed. It always goes somewhere. So it has to start at one of these 10 forms, and it will transfer into one or more of the others. So gravitational, it will heat up the air slightly as this brick is falling. Certainly kinetic, and maybe a bit of sound, certainly when it hits the ground. Chemical, it will produce heat and light, and perhaps a little bit of sound as well. I could have included that. You can just about hear a candle burning, and so on. But a key idea, and I quite like this little image here, where these people are walking up the stairs using the chemical energy in their muscles, turning it into GPE, kinetic, and so on. But it illustrates the idea of this interchange quite nicely, I think. So the unit, as we said, is the joule. So the definition of a joule is a Newton meter. So if you exert a force of 1 Newton through a distance of 1 meter, by definition you are transferring 1 joule. So it might be from chemical to GPE in this case. So again, we have this idea of exchange. So here we've got a ball that's rolling up and down in this bowl. Now we're ignoring friction. We could, if we added friction, heat would come into this. But there's this interchange between GPE, maximum GPE at the top when it instantaneously stops and there's no kinetic energy, to maximum kinetic energy at the bottom. But again, the key thing is the total remains the same at any particular moment. If we freeze it, the total energy will be the same. So here we have obstacles colliding. We saw this in the context of momentum, but we can think of it in terms of energy as well. So let's imagine these have the same mass. So to begin with, the blue one obviously has more energy because it's going faster. It transfers some of its energy to the red one here, and after the collision they have the same amount of energy. Obviously the lines are not on top of each other here, but so you can still see they're separate, but the idea is that they are the same. So here, a slightly more complicated situation. We've got chemical energy that starts off in our little rocket here, and it's getting faster and faster. So its kinetic energy is increasing more and more, and its gravitational potential energy is also increasing. So a little bit more complicated, but the total will always remain the same. All the chemical that gets converted into either of these. And if we add them up, we should see that they always equal the top dotted line. Here we have a car stopping, sort of the opposite of what we saw earlier. Once again, the total should remain the same. So we start off with kinetic energy, and the brakes are screeching and heating up the ground, creating heat and sound. But again, it's the total remains the same. Then we've got a kettle here, so we've got electrical energy being transferred to the kettle, and over time most of the heat, you hope, ends up in the water. Obviously some of it ends up in the air. Now we might use kilowatt hours here to describe the energy rather than joules, which we meant in another video, because the kind of energies exchanged involve millions of joules ultimately if you're running a household for a month or so. So we use kilowatt hours, so 1 kilowatt hour is the energy expended if if you have a 1,000-watt device on for 1 hour. Now, in terms of calculation, we've got 3 key formulas here, but they all come from this one formula here. Energy is force times distance, and again, we covered this in a previous video, some of these points. But very briefly, if we go down this line here, if we realize that force is weight when we lift something up, and that's mass times gravitational field strength. Height is just a type of distance, so instead of saying d for distance, we say h. We end up with this formula, but in essence, the physics hasn't changed. It's just a few of the labels have. And similar thing here, in the context of a spring, the force here is actually the average force, where we just say F, but it needs to be an average force. So the F at the full extent of the spring is the maximum force, so the average is half. So 0 plus the maximum divided by 2 gives us our average. And again, extension is a type of distance, so we put an x there instead of the d. Now, the board won't expect you to follow this derivation here, but for those of you that are interested, you can pause it and have a look and see where it comes from. But in essence, the same thing is going on. We take this formula, we substitute these 3 formulas in. F equals ma, acceleration is change in velocity divided by time, and distance is average speed times time, and we get this, and we tidy it up, and we get this formula here. So the idea is to show that it's the same bit of physics, but it's sort of hidden in these various formulas.